This is ENME351 Lab 8 Op Amps by Garrett Schweitzer. Here's my comparator circuit. So for my code, I am outputting first the voltage going in, the low voltage going into the op amp, and then I am outputting the output voltage coming out of the op amp. So I have 2.5 volts currently as the low. We're outputting 4, the LED is bright. It'll be consistent until I turn this all the way up, and then we're at 5 volts in is the low, which equals the high input, and then we drop down to 2 volts output, and the LED gets very dim. Here I have my derivation for a non-inverting amplifier for the output gain. So we use Kirchhoff's current law and the relations we explored previously. We know the current into each input should be 0 because it's very high impedance. The output current should have no impedance. And using the current law relations, we could find that the gain is 1 plus R2 over R1. Here's my unity gain amplifier. You can see as I decrease voltage, we're maintaining basically the same voltage for the input and the output, which is what we should expect from this type of amp. The only interesting thing is that below a little under 2 volts, it actually separates and the output will maintain that output, even though the positive input might be lower than that. And up at 5 volts, there's a little gap. So I think the slight gap that we have here is because of a rounding error in my code. I think they should be identical to one another. Here's my inverting amplifier. I have the input going at 2.5 volts, the low input, the high input at 5 volts. Now I can move my V in from 0 to 5, and we have this inversion taking place. It's a little under 2 volts and a little over 4 volts is where the plateaus occur with my output values. That seems to be what we should expect. For exercise 4, here is my derivation for the governing equation for the integrator circuit, the integrator amp. So we begin by assuming the voltage of the capacitor is the same as the output voltage, except the opposite, inverse, because of the direction of the capacitor. And then we could use Kirchhoff's current law to figure out that the derivative of the output voltage over time is equal to 1 over resistance times capacitance times the input voltage. We can integrate both sides to get that our V out, our output voltage, is negative 1 over RC, the integral of the input voltage with respect to time. Here is my integrator op amp circuit. So it's very difficult to see with such a high delay, but I tested it on a much slower delay and with input from my end scope. And if I approximate a sine wave, I actually get what's approximately a square wave, which is what we would expect from integrating a sine wave.